Thanks, Mr. Huff, for your intel on Pokemon cards.
Yeah.
Right. Mr. Huff, do you like Yu-Gi-Oh too?
I don't know everything about it. Okay, let's draw a graph. And try to make this as accurate as you can.
All right.
So we're going to graph f of x is 1/3 x to the third minus x. There's a point at 0, 0. There's a point at -1 right about here. Bless you. And there's a point at 1, negative something right about here. There you go. Ooh, hello. So try to draw that graph as best you can. Okay. Just referring back to last time's lesson, increasing or decreasing right here. What do you say? Down here? Decreasing. Increasing. Okay, we're good on that. There's another idea called concavity that talks about how the graph is curving, whether the graph is curving down or whether the graph is curving up. You can kind of think about this like a smiley face or a frowny face if you want to think about it like that. This interval right here, would you call that curving downward or curving upward? So this would be, if you had to describe this as concave down or concave up, what do you think it would be described as?
Concave down.
Concave down, because it's curving down.
Down.
Okay, but this interval right here,
Or it's convex up.
what would you think about describing this part of the graph?
Concave.
Is it curving upward or curving downward?
Up.
So that would be called concave up. That's what concavity is. Okay? But, yeah. I want you to try to draw this as best you can. If I drew a tangent line right here, like that, or I drew a tangent line right there like that, or I drew a tangent line right there. Draw those tangent lines. Come on, focus. Let's go.
Yes, sir. Draw a tangent line.
Draw those tangent lines that I've drawn.
Yeah, we got 3.
Or draw another one right here.
Okay.
Those tangent lines that I've drawn, would you say the graph itself, f of x, is above or below those tangent lines that I've drawn? The graph is below the tangent lines, aren't they? Now some of the tangent lines have a positive slope, some of them have a negative slope, but the whole entire graph on that portion is below the tangent lines, right?
Yeah, correct.
That's a concave down part of the graph. As soon as we switch over here, that tangent line's right here, that tangent line's right there, this tangent line's right there. What happens to the graph now in relation to its tangent lines? The graph is now above its tangent lines. So we describe this part of the graph as a concave up part of the graph. The graph is above its tangent lines here, the graph is below its tangent. You see the difference? Concave down versus concave up.
Yeah.
Okay. Let's see what the first derivative looks like. You guys take like 30 seconds. You find the first derivative. Go.
Okay, yes, sir.
Find the first derivative.
X minus 1.
What is the first derivative?
X squared.
X squared minus 1. Let's clean that up a little bit. Okay. Now I want you to draw a new graph. We're going to actually graph the function of the derivative, x squared minus 1. So the vertex is down here at -1. It has x-intercepts at positive and -1 on the x-axis. What kind of graph are we graphing here, by the way, x squared minus 1? It's a parabola, so graph the parabola. Okay. important to make a few connections here. This that I'm highlighting in blue, that's obviously below the x-axis, right?
Yes.
What is this the graph of, by the way? The red graph that I've drawn here. This is the graph of
The slopes of
the derivative. So this is f prime of x, right?
Yeah.
Yes.
F prime of x is underneath the x-axis between what two numbers?
-1 and 1.
Negative 1 and 1. So would it be correct in saying that f prime of x is less than 0 between negative 1 and 1?
Yeah. That would be okay.
Are we okay in saying that?
Yeah.
Would we also then be okay in saying that f prime of x is greater than 0 on the intervals negative infinity to where? Negative 1. And also,
1, 2.
so that would be this part of the graph here and that part of the graph there. What connection am I trying to make here between the graph of the derivative and the graph of the original function?
The concavity.
The concavity?
Not necessarily.
If you went like this.
What you were saying? Okay. Say that louder. Hey, you guys need to listen to this. Say what you just said louder. Didn't we say that the graph is decreasing right here?
Yeah.
Between which two x values is it decreasing?
-1 and 1.
What does that have to do with the graph of the original, of the derivative function?
Derivatives are below 0.
So the derivative is below 0.
That
Okay?
makes sense.
That's where the derivative is negative, right?
Yeah.
Yeah.
Okay? What do these intervals here have to do with anything on the original function?
The positive.
So it's increasing.
So there
This is where the derivative is positive here and here, right? So on the original graph, shouldn't that mean it's increasing and it's increasing?
Yeah.
Okay?
So you know that -1 and 1 are extrema because that's where it goes from positive to negative on the derivative.
So also, if you find the solutions of the derivative function,
I know that -1 and 1.
Well, I'm going to make one more. I'm just connecting something to last time's lesson, increasing and decreasing.
yeah.
We haven't got to concavity yet.
Okay.
Okay?
Makes sense so far. This seems
Now, take like 2 seconds and find this. Okay. Find it, go.
2x.
You done yet?
Yep.
What's the double or the
double derivative is
the second derivative
2x.
is 2x. Let's graph that one now.
How does that work?
The second derivative is the derivative of the
Oh,
first
that
derivative.
one.
Yeah. What is 2x?
A line
Okay, so
goes up 2 over 1.
where does it go through?
0, 0.
0, 0. The slope is 2.
So what are we finding now?
Okay. Now, this piece of the graph that I'm highlighting in black, that's below the x-axis, obviously. So would I say f double prime of x is less than 0 on what interval? And then f double prime of x is greater than 0 from 0 to infinity. Now I can't fit it all on the same screen here. Hold on a second. There we go. Now I'm talking about concavity with the second derivative. The second derivative helps you determine concavity. This interval from negative infinity to 0, I need you guys to really try to pay attention to this. This interval on the second derivative, negative infinity to 0, the second derivative is underneath the x-axis, or it's negative, right? Now if we go back and relate this to the original graph, here's 0, so this interval right here is the interval negative infinity to 0. What did we say about this portion of the graph in terms of its concavity?
It's concaving down.
It's concave down. Why would we say concave down? Because its second derivative is negative. The second derivative is negative from 0 to negative infinity, right? Or from negative infinity to 0. So this piece of the graph is concave down.
That makes sense now.
Okay? But isn't this portion of the second derivative above the x-axis?
Yeah.
So that's where the second derivative is greater than 0. What do we say about the concavity here?
Concave up. Concave
Why did we say this is concave? It's curving upward, but it's concave up because its second derivative on that interval is positive.
That's cool. That's pretty cool.
Okay?
Oh, so now the change of the slope is now going up at that point. The change of slope is now
Yeah,
going up.
the change of the change slope. Yeah.
What's the first derivative right there with the brown rule? What is, I missed
This first derivative tells you increasing and decreasing intervals. So this first derivative was negative right here. That means the original function should be decreasing in between these two x values because the first derivative is negative. So in between -1 and +1, the function was decreasing right here. Does that make sense?
Yeah.
But now with the second derivative is concave up or concave down. Yeah. It has business applications, mostly economics. I don't know if we're going to get to it in this section, but the concavity,
Well, it's not-
especially inflection
Isn't
points,
that the,
has applications to business and.
that's the acceleration now?
If you're thinking about velocities and acceleration, that would be acceleration, the second derivative.
Okay.
Okay. Third derivative? Well, so let's just write this down in a nice little box here. Test for concavity. Write this down. It's a really easy test, and you got to write fast. Let f be a function whose second derivative exists on an open interval I. We've already discussed what the test is. We just need to write it down in a phrase. The test has two parts. Either because of one condition it's concave up, or because of another condition it's concave down. What were the two conditions? How do we know if it's concave up? If the second derivative is positive or greater than 0, then it's concave up. Okay? So the first condition is if f double prime of x is greater than 0, then f of x is concave up. Well, yeah, let me if f double prime of x is greater than 0 for all x in I, and what is I?
An imaginary state.
An interval. So if f double prime of x is greater than 0 for all x in I, then f of x is concave up. In that interval I. If f double prime of x is less than 0 for all x in I. What does that mean if the second derivative is less than 0 in terms of concavity? Concave down. Then f of x is concave down in I. I'm kind of skipping ahead here in the lesson, but I want to talk about this now while you're writing. The end result of this lesson is just another way of finding extrema. Extrema are minimums and maximums, right? So I want you guys to think about this, because I know some of you can get this answer right away. if you know there's an extreme in an interval, you listening? And you also know that in that interval the graph is concave down, then what kind of extreme is it? So let me ask it again. If you know there's an extreme in an interval, and you also know that that interval is concave down, then what kind of extreme is it automatically? It's a maximum, because the graph is concave down, right? What if you have an interval in which you know there's an extreme and it's concave up? Then it's a minimum. That's the second derivative test. Okay, and that's all it is. Okay? It's not any easier or harder than the first derivative test, just a different way of finding extrema. Okay? So here's an example. Determine concavity of the function here.
Oh, what if we got one and you gotta do quotient first?
Ooh. The one thing that makes these problems fun is how do you determine concavity?
Second derivative.
Second derivative. We'll take a look at this one. Yeah, quotient rule and then a quotient rule. Nice. Well, let's do baby steps. Let's do the first. You want to try it on your own?
Yeah, let's try it. Let's try it. Come on.
I'd say you should let us run three and then correct our
put on our
mistakes.
pull-ups, take off the diapers, and scream out that we're a big kid.
All right, try the second derivative.
Except we still play
Go.
Yu-Gi-Oh.
Put away your Yu-Gi-Oh cards.
Someone's here watching that video like, what the heck?